So welcome to this video from myself, James, from Electronics for Engineers. This video will show you how to draw pretty much every phasor you'll come across in electronics, and I hope you enjoy watching. With phase vectors or phasors, the length of the vector, or the radius as I've shown it here, is the amplitude or peak value of the voltage or current. But don't forget that voltage and current have different scales. The angle of the vector is the phase of the voltage or current with respect to the reference vector on the x-axis. And phasors rotate anti-clockwise with an angular frequency of omega, which is in radians per second. Omega is equal to 2 pi, the angle in a circle, multiplied by how frequently we spin through a circle. Here's a graph of y equals sine x, which is like what our resistor voltages VR are like. It has a period t of 1 divided by the frequency in hertz, and the period is in seconds. It has a zero phase shift because it starts at the origin and it is increasing at that point. The angle in one cycle is equal to 360 degrees or 2 pi radians, roughly 6.3 radians, because a radian is around 57 degrees. Our inductor voltage has the same period, and if we break the period up into a period divided by 4, then the time difference with this waveform, it looks as though it's ahead by a quarter of a period, which represents a phase lead of 90 degrees compared to a normal sine wave. This is a graph of y equals sine x plus or minus 180 degrees. It has the same period as all the other waveforms, and it's said to be in antiphase with a normal sine wave. We could see it as starting with a lead of 180 degrees or half a waveform, or we could see it as starting 180 degrees later compared to a normal sine wave, or having a phase of minus 180 degrees. Either way, it looks the same. And this is actually a graph of y equals minus sine x. It's an upside down sine wave. The capacitor voltage, Vc, we could use the equation y equals sine x plus 270 degrees, because this sine wave looks as though it started 3/4 of a period ahead, which would have a phase of 270 degrees leading. But we could see it as if the time difference compared to a normal sine wave is minus a quarter of a period, or having a phase lag of 90 degrees. And in electronics, this is how we view capacitor voltages. Our supply voltage is at an amplitude of 100 volts. The series current, IS, which you could call the total current if you like for a series circuit, is 91.61 milliamps in amplitude. It has a phase of 0 degrees. So on our phasor diagram, the series current would live on the x-axis where there is a 0 degrees or 0 time has passed. On our phasor we can show 90 degrees or a quarter of a period, 180 degrees or half of a period, and finally we can show 3/4 of one whole cycle, which is equivalent to 270 degrees. Our current IS had a magnitude of 91.61 milliamps, and it had 0 phase because it was our reference vector. More on that later. Omega is our angular frequency. Our resistor voltage was measured, say, at 91.61 volts. That's its amplitude or peak value. Because it has 0 phase, it lives on the x-axis, and the length is proportional to the voltage, the length of our vector. Our inductor voltage VL, say it was measured as 76.36 volts. It has a time period lead of a quarter of a period, or it has a phase of plus 90 degrees. It's ahead of a normal sine wave. So because it's 90 degrees ahead, more on that later, but we put it on the y-axis, the positive y-axis. Finally, our capacitor voltage, say it was measured as 36.27 volts peak, then that is said to have a phase of minus 90 degrees, or a phase lag of 90 degrees compared to the series current and the resistor voltage. That's like having a time difference where it starts its period a quarter of a period later. Instead of saying it has a phase of 270 degrees though, we say it has a phase of minus 90 degrees because they are equivalent to each other. We know what supply voltage we put into our circuits because we put them in with a signal generator, but what is the phase of the supply voltage in this series circuit? Well, how we do it is to find the y-axis resultant, which involves the inductor voltage and the capacitor voltage. We take VC away from VL, because the capacitor voltage is negative compared to the inductor voltage, and we're left with a y-axis resultant of 40.09 volts. Then we can resolve this triangle to find the phase of the supply voltage. The phase angle between the current and the supply voltage is the opposite side divided by the adjacent side, but we take the inverse tan of that figure. So it's tan to the minus 1 of the y-axis voltage resultant divided by the x-axis voltage, and there's only one x-axis voltage. And this comes out as 23.63 degrees for this particular example. There's our phasor diagram for our series RLC example circuit. If we want to, we can show it as a voltage triangle instead. And these are the formulas or equations for the mathematicians out there. These are the waveforms that I've made into Desmos graphs, and see the links in the description for these graphs. This is my series RLC graph. We can change all of the attributes and it'll show us the graphs on the fly. I've done the same for the parallel RLC circuit as well, which we'll look at shortly. With the series RLC graph, that web link, if you want only a resistor capacitor circuit, then make the inductor value very, very small, say 1 × 10⁻⁹ Henry. For a resistor inductor circuit, make the capacitor massive. And change the supply voltage, the resistance, inductance, capacitance and frequency as required. For the parallel RLC graph, do the opposite to the above for a RC or an RL circuit. CIV is a way of showing us how voltages and currents are out of phase with each other in capacitors and inductors. For a capacitor, the current leads the voltage, or I leads V, so it's IV. Think of capacitors as IV growing down, if you like. Current starts first, and then the capacitor voltage builds up afterwards. So current leads voltage for a capacitor, IV. For inductors, it's the other way around. For an inductor, the voltage leads the current, or VIL, because L is the letter for an inductor. And think of VI or VI. A pair of eyes made of inductors maybe, where the voltage starts first and the voltage leads the current for an inductor. These graphs show us how voltage and current change with frequency for capacitors and inductors. For a capacitor, as the frequency increases, the capacitor voltage goes down. And as the frequency increases, the capacitor current goes up. The opposite's true for inductors. As the frequency increases, the inductor current goes down. and as the frequency increases, the voltage across the inductor also increases. Now, steady state versus transient state. Transient state is like when you start your car up, and the steady state is when your car is idling smoothly. Phasors are for the steady state. You can see these circles which show where the voltages at the transient part, where we just start our circuit, don't match the steady state. If we zoom into the very start, CIV breaks down here. The early transient state, the series current, or the current of the circuit, and the supply voltage, and all the other voltages are positive and rising, and nothing has peaked yet, so they're basically in phase. CIV is only for the steady state, and phasors, whenever we talk about phasors, we're talking about the steady state when everything's settled down in the circuit. I'm going to base my phasors on RLC circuits to start with. A series circuit has a common current. Each component has the same current but different voltages. So there's our supply current, IS, and that's the same current through every component. This could be our phasor diagram. We always put omega on the angular velocity in radians per second. There's our supply current, which is equal to all of the other currents, but we just put IS to make it nice and tidy. Resistor voltage and resistor current are always in phase with each other in any circuit, but for the inductor, voltage leads ahead of the current. So the inductor voltage is 90 degrees ahead of the current through it always. The series current lags behind VL by 90 degrees or a quarter of a period. But the opposite is true for the capacitor voltage. With a capacitor, current leads voltage, so it looks as though the capacitor voltage is 90 degrees behind the series current, which it is. But we say in terms of current lagging or leading. The current leads ahead of VC by 90 degrees. If we have a larger inductor voltage, this means we must be at a higher frequency. We can show the supply voltage and work out the phase angle. So this would be higher frequency or with a larger capacitor or a larger inductor. This is an inductive circuit at this frequency because the supply current is lagging Vs. If we're at a lower frequency, say, and we have a larger capacitor voltage than the inductor voltage, then the supply current is clearly leading the supply voltage because these spin anti-clockwise. This is a capacitive circuit at this frequency. Now for the parallel version of an RLC, there's a common voltage across all components instead of a common current. Each component has a different current. We put our reference vector, which is the thing that everything shares in common, which is Vs, on the x-axis, and everything is relative to that. The resistor current is in phase with the voltage across it always. The inductor current lags the voltage across it. And the capacitor current will lead. So IL lags behind Vs. But the capacitor current leads ahead of Vs. With a larger capacitor current, this would be at a higher frequency. With a large capacitor or a large inductor, the current is leading the supply voltage. At a lower frequency, the supply current will be lagging the supply voltage. So this would be at a lower frequency or with a smaller capacitor and smaller inductor. IS is lagging VS. Voltage and current are always in phase in any circuit for a resistor, and we'll look at the waveforms. From Ohm's law, we know that the voltage across a resistor is equal to the resistance times the current. We zoom in here, and at all points, the voltage and the current are at the same part of their cycle. Here, VR and IR are 0. At this point, they're both at their negative maximum value. There's no phase difference. And again, VR and IR are at 0 here. They're always in phase in any circuit. For an inductor, it's much different though. We know that voltage leads current, VI, for an inductor, and the voltage across an inductor is equal to the inductance times the rate of change of current. So when the gradient of current is at its positive maximum value, then the inductor voltage must also be at its positive maximum value. When the gradient of current, di dt, is 0, it's flatlined, VL is 0. When the gradient of current is downhill and steep, it's at its maximum negative value, VL is at its negative peak value. And again, when the gradient of current, the rate of change of current is 0, VL is 0. And that is why voltage leads current for an inductor. For a capacitor, we know that the current leads the voltage. And that is because the capacitor current is equal to the capacitance times the rate of change of voltage. Not the voltage itself, but the gradient of voltage. When dV dt is at its maximum positive slope, the capacitor current is at its maximum value. When the gradient of voltage is 0, it's flatlined at the peak. IC is also 0, the capacitor current. When we have a maximum negative slope of the voltage with respect to time, then the capacitor current is at its negative peak value. And finally, the rate of change of voltage is flat or 0 here, so IC is 0. And that is why current leads voltage for a capacitor. So with an RL circuit, a resistor and inductor, we have the common current, IS, and the voltage leads it across the inductor by 90 degrees, but VR and IS must be in phase. We can resolve these vectors to find the supply voltage and find the phase angle by simple trigonometry. It's equal to tan to the minus 1 of VL over VR. And this changes with frequency. For a capacitor, the current through it leads the voltage, so the voltage lags the current, if you like. And again, we can make a voltage triangle, and the phase angle is negative here. Be careful, because the capacitor voltage is always negative with regard to the inductor voltage, so we need a negative angle here below the x-axis. With a series RLC circuit, there's just one current. We show VR and VL and VC. Here we have an inductive RLC circuit, which would be at high frequencies with a large inductor or a large capacitor. And we can work out the supply voltage and the phase angle as we did before. Remember that BC is negative, so we're taking away the magnitude, or we're doing simple vector addition, VL plus a negative VC for the opposite side. For a capacitive RLC circuit, that just means that we'd be at a lower frequency or with a smaller inductor or smaller capacitor. and now the current leads the supply voltage. At series resonance, the impedance of the circuit, which impedes current, is at its minimum, so we have our maximum current, but VL equals VC and VS equals VR. And the current is in phase with the voltage at resonance. So going back to our RL, we can see that the supply current lags the supply voltage for an RL circuit. That's always true. For our RC resistor capacitor circuit, the supply current leads the supply voltage, and that is always true as well. For the series RLC, the lag or lead of the current depends on the frequency. At high frequency, the current lags the supply voltage. At lower frequency, the supply current leads the supply voltage. And at the resonant frequency, the supply current and the supply voltage are in phase. We can't even see the supply voltage on this graph because it's completely underneath the resistor voltage. And the voltages of the capacitor and inductor are equal at the resonant frequency, and we have our maximum current. So now for the parallel versions. With a parallel RL circuit, the inductor current lags behind the supply voltage. Or we could say the supply current lags VS. We can zoom in onto these waveforms. I made these on multisim.com. IS lags VS for a parallel RL circuit. For a parallel RC circuit, remember we have a x-axis reference vector of voltage, and we can see that the capacitor current leads the supply voltage. So the supply current also leads the supply voltage, and phase differences between the supply current and the supply voltage. Now we can see the supply current is ahead of the supply voltage in time and angle. Now for our parallel RLC circuit. Be careful when we say inductive, because at higher frequency, or with a large inductor or large capacitor, it's the capacitor current that is dominant at high frequency. So this is the opposite to a series RLC circuit. Let's look at those waveforms. So IS leads VS at higher frequencies for a parallel RLC circuit. Now at lower frequencies, the inductive reactance is smaller, so that means the inductive current or the inductor current is larger. So a capacitive parallel RLC circuit has a larger inductor current. It's a little confusing, but it's the opposite of the series versions. So the supply current lags the supply voltage at lower frequency in our parallel RLC circuit. Finally, the resonant frequency of our parallel RLC. The impedance is at a maximum, so we have a minimum supply current, and that is equal to the resistor current, and IC and IL are equal. We can look at the waveforms for this as well. So IS is in phase with the supply voltage, and IS also equals the resistor current, IR. Let's make some quick animations to explain it a bit further. So V and I are Gambu, they're best friends, they're always in phase with each other for a resistor. Now for our inductor only circuit. It's kind of like a racetrack, but of course phasors are drawn around a rotating circle, not an oval. And now for our single capacitor circuit. Series and parallel RL phasors. So with our series RL and parallel RL, these are the analogies to what we looked at earlier on a racetrack. Supply current for the series circuit is the reference vector. Everything else is with respect to the reference vector IS. For the parallel circuit, the thing in common is the voltage across the components, so that is on the x-axis to the right of the racetrack with 0 degrees phase. Everything else is with respect to the reference vector on our x-axis phasors. Series and parallel RC phasors. For the series RC circuit, the thing that it has in common is current, so the supply current goes on the x-axis with 0 phase. And remember, the voltage across the resistor and the current through it are always in phase in any circuit. For the parallel RLC, the thing the components have in common is voltage, so that goes on the x-axis of our phasor. And the resistor current is in phase with the resistor voltage. But there's only one voltage in this parallel circuit, or in any parallel circuit. Now looking at RLC at low frequency, series and parallel. The common current for our series circuit lives on the x-axis as ever. So there's IS. There's VL. It's quite small at low frequencies. VC is large at low frequencies. The resistor voltage is dictated just by the resistance, and our current is leading in this example at low frequency. The current leads the supply voltage. And because it's low frequency, they're spinning more slowly. Now for the parallel circuit, the components have a common voltage across them, so that is the reference vector on the x-axis, Vs. We have a large inductor current, a small capacitor current, and the resistor current is dictated only by the resistance. Resistors aren't reactive, so they don't care what the frequency is. Our supply current is lagging at the moment at this frequency. Now for RLC at high frequency, series and parallel phasors. So for our series circuit, the common current is the reference vector. Everything else is with respect to that. With series circuits, you get a voltage triangle, and with parallel circuits, you get a current triangle. At high frequency, VL is larger than VC, and our current is lagging Vs at high frequency. For the parallel circuit, our supply voltage, a small inductor current and a large capacitor current. The current is leading now at high frequency. And now for the resonant frequency, series and parallel RLC phasors. There's our supply current at its maximum value for series resonance. VL is equal to VC at resonance. VR goes on the x-axis, and the supply voltage equals the resistor voltage at resonance. Now the parallel RLC resonant frequency circuit. IL is equal to IC. The impedance is at its maximum, so the supply current equals the resistor current in phase, and they are at their minimum values. These are just the colours that I use, which may help you. I didn't want to put all of these formulas at the start of the video, but feel free to pause on them and double check. You can ask any questions in the comments if you want to understand why things have been in this video. But I've put a lot of formulas here which will help you if you get stuck with any of your calculations. So there's the inductor and RL, the capacitor and RC, series and parallel RLC. And I hope you found this useful. Thanks so much for watching. Please comment, and all the best.